meters per second. If the work on the bullet is done over the distance of 0.75 meters, what is the average force on the bullet? Now, the video that you watched before this actually talked about energy and work. And for a person to do energy, then in that case, for a person to do work, they must have energy. So once an object has energy, or a person, then they can do work, which causes the ability to move an object. Okay? Now, because those two words are related to each other, like impulse and momentum, and we can set momentum equal to impulse, the same thing here, where we can set up, and let me write this down let's write it down over here on the side, because energy must be there so work could be done. They are related to each other. They are so related that we put them equal to each other. And we can say work, I don't know why I put E, K, equals KE, kinetic energy. Because when work is done, movement occurs. Okay? Now, just like those equations with momentum and impulse, we can break this apart into its components, or we can say we can derive a new equation from it. So we can say that work equals force times distance, which equals kinetic energy 1/2 mv squared. That is our equation. We call that the work energy theorem. That's what the equation is called, work energy theorem. So using the work energy theorem, we need to find the amount of force. I know that work equals kinetic energy. And so I can break this apart to say that force times distance equals 1/2 mv squared. We're looking for force. Do I have distance? Check. Do I have 1/2? That's a constant. Check. Do I have mass? I do, but I must King Henry it. And I have velocity. Yes, I do. So let's come over here, and I'm going to first King Henry. King Henry drinks utterly delicious chocolate milk. I'm going from grams to kilograms. Grams is at the base unit. Kilograms is over here. That means I'm moving to the left. How many directions or how many spots? 1, 2, 3 spots to the left. Here is my number, 4.2. Let's move it 3 spots to the left. 1, 2, 3. My new decimal is right here, and I fill in those little bubbles with zeros. So this is my new number in kilograms. That doesn't count anymore. So let's go ahead and solve for the force. F multiplied by 0.75 equals 0.5, which is the same thing as 1/2, times the mass, which is 0.0042, times the velocity, which is 965 squared. Now that I set you up, I know you can finish the rest of the math. Divide by 0.75, cancel. Divide by 0.75. Force equals blank newtons. Please don't forget to square that number. And I'm going to just do this because I'm going to set you up, but I'm not going to work it out all the way to the end. All right, I'm expecting you to. Next one. A hockey puck is accelerating using a hockey stick over a smooth, level ice surface. Now, the puck has a mass of, which is in kilograms, so that's a good number, and is moved by the stick for a distance of, which must be in meters, so distance is a good number. What is the average force? Question mark F. If the final speed of that hockey puck was 25 meters per second. Again, we're going to use the work energy theorem. So work equals kinetic energy is how it's written out. But we can expand to force times distance equals 1/2 mv squared. And so in that case, since I'm looking for force, I'm going to multiply it by 0.8 equals 1/2, which is also 0.5, times the mass of 0.4 times the velocity of 25. Please don't forget to square it. Now you need to do your algebra and solve for F, which I know you can finish that off. It's going to just take practice is what it's going to take. Let's keep going. Kinetic energy practice. So all of those questions are kinetic energy. Question number 1. Question 1 says that a 7-kilogram bowling ball moves at a velocity or speed of 3 meters per second. That is the mass, and it must be in kilograms. How much kinetic energy does the bowling ball have? Question mark KE. I'm going to go ahead and write it over here for you, but my equation for KE, just in case if you just don't have it or know it, KE, and we just talked about it on the previous page, equals 1/2 mv squared. Okay? So you need to solve for KE. So KE equals 1/2 mv squared. And here's your m and there's your v. Solve for it. Next one. How fast must question mark v. I'm actually looking for the velocity. Must a ping pong who has a mass of 0.0025 kilograms, kilograms is a good number, move in order for it to have the same kinetic energy as the bowling ball? So in this case, you're going to use the same equation, but instead you're looking for velocity. So whatever the KE is over here, you're going to bring it over here and you're going to plug it into the equation. KE equals 1/2 mv squared. You're going to solve for velocity. Do not forget to square root it. This page is worth 10 points. Next one, starting from rest, Kirk zooms down a frictionless slide with the initial height of 7 meters distance. What is his speed halfway down the slide? Oh, I like that. Question mark his speed or velocity, but we only want it halfway down. What is his speed at the bottom of the slide? Question mark speed at the bottom. Ooh, I like that. Okay, so I know that when an object's falling down, gravity's pulling down, the object's moving down, it's speeding up. So at the bottom, there is a velocity. And the only physical number that they gave me was 7 meters, which is crazy, right? That's it. Isn't kinetic energy 1/2 mv squared? I don't have Kirk's mass. I don't have his velocity. Oh my goodness. But that's okay, because I know that due to the law of conservation of energy, I'm going to have what we call the mechanical energy for a system. And whatever the mechanical energy is for that system, it's going to be the same at every location of the system. So in this case, if he's at the top, and let's pretend he's at the top because he starts from rest, and that's his velocity 0 at the top, then I know that I can use the potential energy equation, and I'm going to say PE equals mgh. His mass, and I guess that's where now I see that there's a problem. Well, I'm glad you're watching the video, because we definitely need the mass of Kirk. And Kirk actually has a mass of, and let's go ahead and write that in. Kirk's, let's do an arrow, mass equals 125 kilograms. He's not a skinny guy, let's say that. So 125 kilograms. So I'm going to say 125 times 9.81 times 7, because that's how high up he is. Now that's going to be the potential energy. But at the top, his velocity is 0, so his kinetic energy is 0. So if I find the potential energy at the top, then I'm going to know what the mechanical energy is going to be. So let's go ahead and do that. 125 times 9.81 times 7, because that's how high up he is. The mechanical energy is going to be 8,583.75. Now that's mechanical energy. Now, question number 3 says, what is his speed halfway down? So if I know his mechanical energy, okay, now we can go ahead and figure that out. His kinetic energy halfway down, which, what is 7 halfway down? All right, 3.5 meters. So let's do KE at the 3.5 meters. Let's do that instead. And that way we can find his, what do you call it? His velocity. We can go ahead and at halfway, wouldn't his potential energy be half of this and his kinetic energy be half? Does that make sense? Because if his mechanical energy at any given point is this number, and they want to know about the halfway mark, and if we're halfway, half of his energy is potential, the other half is kinetic, combine them together, that equals mechanical. So I'm going to come over here for question number 3, and let me go ahead and do some more work over here for you. I'm going to get 8,583.75 and divided by 2. That is going to equal his mechanical energy cut in half. So 8,583.75 divided by 2 actually comes out to 4,291.85. Now that is half of his energy, and that's where we want to look at halfway point. So I'm going to use now, because this was step 1, this was step 2. Now step 3 is to say KE equals 1/2 mv squared. His KE is going to be at the halfway mark, 4,291.85 equals 0.5 times his mass, which is 125 kilograms, times his velocity squared. And I don't know it, but I can solve for it. Divide by, so 125 times 0.5 actually ends up being 62.5. That cancels. Divide by 62.5, 4,291.85 divided by 62.5 comes out to a velocity squared of 68.67. And we're looking for velocity, so we're going to have to square root it. So second key square of 68.67 comes out to the velocity of 8.29 meters per second. That is his answer, or that is my answer for this question. Now, what is his speed at the bottom of the slide? Well, in that case, since we know the total mechanical energy is 8,583.75, we can just say that this number equals 1/2 mv squared, and we can solve for the velocity at the bottom, because at the bottom his potential energy is going to be 0. So all of his energy is going to be converted or switched over to kinetic at the bottom. And this is all of his energy at the top for potential only. So now we know that M is going to be 125. So I'm going to put 125 right here just to conserve space. 125 times 1/2 or 0.5 comes out to 62.5. 62.5. This cancels out. Get this number and divide by 62.5. So 8,583.75 divided by 62.5 comes out to a V square of 137.34. Not my answer, because that is a V square. I must square root this number, and I know there's not a lot of space. I'm so sorry. Do your work over here in the margins if you need to. But second key square of 137.34 comes out to a velocity of 11.72 meters per second. And that is his answer for the velocity at the bottom, which if you stop for a moment and take a look, this is his velocity at the halfway mark. This is his velocity at the bottom. Wouldn't he have a higher velocity at the bottom? Yes. And look, mathematically, we got a higher velocity. I am going to need you to attempt and to do number 4 and number 5. Okay? You need to try some of this on your own. Okay? The next one. A 1,500 kilogram car is traveling at 25 meters per second. They gave me the mass in kilograms. They gave me the velocity. Now, the brakes are suddenly applied and the car slides to a stop. The VF equals 0. The average braking force between the tires and the road is actually 7,100 newtons. How far, question mark, distance, will the car slide once the brakes are applied? Well, again, when we're offered or given this much variables, it's more than likely going to be the work energy theorem, meaning that work is equal to kinetic energy. Work is force times distance, and kinetic energy is 1/2 mv squared. We are looking for the actual distance. Did they give me the force? Yes, they did. 7,100. The distance, I don't know it. 1/2, I'm going to change it to 0.5 because it's easier to work with decimals instead of fractions in physics. The mass of the car is 1,500, and the velocity of this car was 25, but don't forget to square the velocity. Now, in this case, you can go ahead and do the algebra. Divide on this side, cancel, divide on this side. All right. And now you can go ahead and solve for the distance, which should be in meters. Almost done. Almost done. If I didn't, which I don't think I did, let me go ahead and box this in. This is mandatory that you do this. I did a big chunk of this already for you. You only have to do 4 and 5 on your own, and you just need to finish solving this. That's it. Okay, I'm trying to help you out and do as much with you on this foldable because I want to make sure that I'm helping you out. This is a big unit. Normally it's divided into 2, but unfortunately we have 2 units combined. Now, elastic potential energy. Again, I'm videoing this on Wednesday, and we haven't talked about elastic potential energy, but it sounds like the word elastic, where if you have something elastic, you can stretch it apart. But the word elastic potential energy also has the ability to smush together. For an example, I got a clicky pen. What is causing my clicky pen to work? What is inside of there? I know that every one of us has probably took apart a clicky pen. And what do you know that's inside of there? The spring. A spring can be, look at this, compressed. And now that it's compressed, if I push it again, it's going to stretch apart. So that's what elastic potential energy is. It is the energy with stretching or compressing an object together that can go back to its original form, like a spring, like a rubber band, like a bungee cord, like a hair tie, a scrunchie. All of those, the elastic in your pants, all of those are elastic potential energy. Now, elastic potential energy has an equation, and for that equation, elastic potential energy, I'm going to put it over here. We call it PEE equals 1/2 times lowercase k, not capital, times d squared. Now, the lowercase is what we call a spring constant. The spring constant is a constant for every single material out there. So haven't you, and I don't know about boys, but girls, when you get a hair scrunchie or a hair tie, there are some hair ties that I don't buy because they don't have a lot of elasticity with them. They're not going to hold my hair very well, okay? That means that it has a lower K value. But a hair tie or a scrunchie that's really firm and that it's going to hold my hair because it's really tight has a higher K value. So because they're made of different materials, they're going to have a different K value. The distance is how far you stretch it apart or how much you smush that spring together. Okay, so let's do a couple of practice questions over here. It says here, and that is the last page, a spring is stretched at a distance of 0.2 meters. That is a good distance number from equilibrium. The force or the spring constant K value for this spring is 2,500. What is the potential energy? This is my K value. Question mark, what is the PEE? PEE equals 1/2 times K times distance squared. So I'm going to go ahead and change the 1/2 to 0.5. The K they told me, which is a Newton meter of 2,500, and the distance is 0.2, but don't forget to square that 0.2. And now you can do the math. What is the SI unit for PEE? Anything that has to do with energy, the SI unit is in a joule. So please solve for that. The next one, a spring has a spring constant of 500 Newton meters. That's the K value. What is the potential energy, the PEE, question mark, that's stored in the spring when it's compressed to a distance of 0.05 meters? Alrighty, so let's go ahead and let's do that one. PEE equals 1/2 K D squared. And they gave me all my information. I'm going to change it to a 0.5. The spring constant is 500. The distance is 0.04. Do your math and get your answer in joules. Using the same spring from the question above, what is its potential energy when it's compressed to 0.03? So now if I'm going to compress it a less distance, show your work. So 0.5 times 500, which is the K value. And forgive me, look right here. I forgot to square it. Please don't forget that. I made that mistake. 0.03 squared equals blank joules. Does more or less compression distance result in a higher potential energy? You need to do those two answers so you can answer letter B. How much potential energy does the spring have when it's at rest with no compression? So you need to kind of think about that and do that question. Then the last one is going to be another work energy theorem. And I want you again to practice that one on your own because I've already done all of the other ones with you. So I'm going to now highlight this part because when I'm grading, I'm going to look at those to see, did you go back and you finished it off? This page is worth 10 points, okay? Other than that, now I'm done with the foldable. This is for a grade. You know when it's due. And if for some reason you're out because of COVID or because of you have a dentist appointment or something, then you still must turn this in then through email every single page, and I need to be able to see it. Don't do some crazy picture that's 7 feet high above it and I can't read the actual page, okay? You know what the points are. Please make sure you turn it in on time, or if you're going to be out, then you need to email every single page to me on time. What is considered to be on time? You need to make sure that it's sent to me by the time your class starts. So if your class is a Wednesday at 11 o'clock, then you need to make sure that you email this to me by Wednesday at 11 o'clock, or it will be counted late, minus 20 points off. Alrighty. Other than that, you have a great day.